simplifying and working with radicals, the first thing that we need to do is make sure that we understand the difference between rational numbers and irrational numbers. According to the formal definition, a rational number is a number that can be expressed in the form A over B, where B is not equal to 0, because we all know that you can't have a 0 in the denominator of a fraction. Technically, this definition includes all numbers whose decimal repeats or ends. So terminating or repeating decimal. And if we look at some of the examples, all of the numbers that you've been using since you were a little kid, like 5 and 3, those are examples of rational numbers. And then because of the definition, according to this, any fraction is also going to be considered a rational number. So that A over B is defining any fraction, and it doesn't matter whether the bigger number is on the bottom or the bigger numbers on the top, those are still considered fractions. The only thing that can't happen is you can't have a 0 on the bottom. And it can be the positive or negative of these numbers. It doesn't matter. It can be decimals that end, for instance, 27.3, or it could be 27.3 where the 3 repeats forever. Could be a fraction like 17 over 312. Doesn't look very rational, but it is, because you can write it in the form of a fraction. Irrational numbers are numbers that cannot be expressed as a fraction. So cannot be expressed as A over B. Those would be numbers that include radicals that cannot be simplified. So I'll give you an example here of radical 2 or radical 3 or radical 17. Radicals that we can't take the square root of because the numbers underneath are not perfect squares. In addition, probably somewhere in middle school you talked about the most famous irrational number that there is, which is pi. Now pi has decimal values that go forever, they never stop. A lot of times we round that decimal to 3.14, but technically the decimal goes on and on forever. So we're distinguishing the difference between these two because we are going to be asked in this unit to simplify any irrational numbers that can be simplified. So when we go through and do that, one of the first things that you want to make sure that you're aware of is what the numbers are that are perfect squares. Perfect squares are numbers that you automatically know the square root of. For example, 9 is a perfect square because we know the square root of 9 is 3. Other ones, they're 4, 16, 25, 36, all of these numbers because you can square root them. 49, 64, 81. I'll add on here 100, and then 121 and 144. So at least if you have those memorized up to 144, square root of 144 is 12, that at least gives you a good set of perfect squares to work with. Now, according to square roots, those square roots have an index of 2, and this may be something that you've never talked about before. And I'll give you an example of what that means. When we take the square root of 49, we automatically know that that answer is 7, because 7 times 7 twice, multiply 7 times itself twice, gives us 49. So the 2 for the twice that we multiply 7 together is the index. We generally don't write that. It's understood that if we just have the square root of 49, we know the index is going to be 2. The reason why they're mentioning that here is because it's possible to have another index. And I'll give you an example of what I mean. It is possible for you to have an index of 3, let's say, where you're looking for what number do you multiply by itself 3 times to give you 64. So in this case, because the index is 3, whatever the number is has to be multiplied by itself 3 times. The to this is 4. So the cube root with the index of 3 is going to be 4. So they're kind of trying to get you to notice that the index of 2 is really what we want to be working with here. If by chance you're working with numbers and you don't know the factors of them, it is always possible to take whatever number you're working with and put it into your calculator using this. So go to your y equals button, and then whatever the number is that you need to know the factors of, divided by x. So I'm going to pull up my calculator here, and let's suppose that we were looking for all of the factors of 72. So I would type in y equals 72 divided by x, and then I would hit the second graph button, which takes me to my table, and I can see what all the factors are. I can arrow up for factors that are close to 1. We know 1 goes into 72, but we're not going to use that. So we can see that 72 divided by 0 doesn't work. 72 is divisible by 1, but we're not going to use that one. It's divisible by 2 times 36, 3 times 24. And then we can see that when we try to divide 72 by 5, it doesn't go in evenly, so we wouldn't end up using that. So this is going to be a list of all of our factors. So keep in mind, if you don't know the numbers, use your calculator and go through and take a look at the set of factors. So I'll put here, you're going to go to your table to see that set of factors. So for our little example, what we did is y equals 72 divided by x. And that gave us all of our factors of the number that we were talking about, which in this case is 72. So I've kind of given you a little bit of background. Now we want to actually go in and start doing the simplifying of the radicals. So we're going to start with question number 1. And for question number 1, if we have to simplify radical 8, what that means is we've got to look at the factors of 8 and try to find one factor that we know is on our list of perfect squares. So as soon as I look at this, I know that 4 is a factor of 74. I'm sorry, 4 is a factor of 8. So when I go through and do this, I know that I can take the 8 and split it up into 4 times 2. Once I do that, and again, the reason why I'm picking the 4 is because it is a perfect square. I can divide them up and give both of them their own radical. And then from there, the square root of 4 is 2. And the square root of 2, we can't simplify further. It's on our list of irrational numbers, so we cannot simplify that further. So technically, what this means right now is that this radical 8 that you have here and this 2 radical 2 that you have here are equal to each other. The radical 8 is in the unsimplified form, 2 radical 2 is in the simplified form. So the rule is that you cannot keep a radical with having a factor that's a perfect square. You have to make sure you go through and simplify that out. So let's go ahead then and take a look at question number 3. In question number 3, I'm looking for the factors of 48. If I was to go through and make a quick list of them, I know that this is my list of factors. I also have 4 and 12 here. And I want to find the set of factors that have the biggest perfect square. So as I'm looking at this, I know that I have a perfect square right here with 4. But this 16 is my biggest perfect square. So I want to try to pick that one so that my steps of simplifying go a little bit quicker. So I'm going to use that perfect square of 16, and I'm going to break 48 up into 16 times 3. I'm going to give them both their own radical, radical 16, radical 3. And the reason why I picked 16 is it's on my list of perfect squares. The square root of 16 is 4, and this answer is 4 radical 3. Again, what this means, radical 48 and 4 radical 3 are equal to each other in their value. Radical 48 is not simplified, 4 radical 3 is. So let's go ahead then and take a look at, let's do question 5. So as I'm looking at question 5, I have to split up 80. I want to look to see what all the factors of 80 are. Some of you may know those off the top of your head. Some of you may need to use your calculator when you go through and do that. The 3/4 that's out front may be kind of bothering some of you. Technically, what that means is it's 3/4 times radical 80. So the 3/4 is just going to carry along until I find another number that is outside of the radical, and I can't get that until I simplify the radical 80. So I'm going to split radical 80 up into 16 and 5, 16 being the largest perfect square that goes into 80. So this is 3/4 times, remember there's multiplication in there, square root of 16 is 4, radical 5. And this ends up giving me, when I multiply the 3/4 times the 4, the 4's cancel, and I get 3/1, which is just 3, radical 5. You want to make sure when you're doing these, you do not skip steps. If you try to skip steps, you're going to be more likely to make mistakes. So far we've only talked about numbers being underneath the radical. What you need to know is that exponents can appear there as well. So if you take a look at the next section, it talks about what happens when there's variables underneath the radical. So if we have variables under the radical with exponents on them, it's classified into two categories, type A and type B. Type A is when your exponent is even. So if your exponent is even, the rule is that you're taking square root of a variable with an even exponent, that your answer to that is going to be x to the whatever your even number is divided by 2. So if we take a look at question number 7, x to the 8th then would be equal to x to the 8 divided by 2, which is at x to the 4th. For question number 8, if we did that same thing, x to the 22 is going to turn out to be x to the 11th, 22 divided by 2. So it's an extremely easy process when you go through and do that. For question 9, a little bit different here. We not only have a 49 under the radical, but we also have an m to the 20th. 49 is an actual number. So the square root of 49 and then the square root of m to the 20th, you may find it easier to kind of simplify or separate those into two separate radicals. Square root of 49 we know is 7. Notice I'm square rooting that because it's a whole number. But the square root of m to the 20th, I'm going to divide the 20 by 2 because that is an exponent. Take a look at the next page, you can see that there's a couple more examples here at the top that may tend to be a little bit more challenging. If you take a look at number 11, same idea here. We want to make sure that we're kind of looking at the numerical part separately from anything that has an exponent. And when I square root a fraction, I square root the top number, square root of 16 is 4, and square root the bottom number, square root of 9 is 3. And then square rooting the exponent is going to give me x to the 9th. So I'm dividing that 18 by 2. So I'm going to flip back now and write in the rule for when the exponent is odd. It's kind of the same thing. We just have to separate the evens and odds apart from each other. So if we go ahead and we take a look at this, if our exponent is odd, this is the second option. What we're going to do with that odd exponent is we're going to split it up into x to the most amount of evens we have, followed by x to the first. So I'll give you a little example here on this side before we flip this over. So let me give you an example. Let's just suppose that we have the square root of x to the, I don't know, even 19th. We're going to take the most amount of evens we can out of 19, which is 18. And that's going to leave us one extra left over. So an x to the 18th and an x to the first. Now the square root of x to the 18th falls back into the rule for the evens, which is going to be x to the 18th divided by 2, which is 9. And then we have an extra radical x here. So our final answer, x to the 9th radical x. Please flip your paper over and let's take a look at a couple more examples on the back here. Let's start with an easy one. Number 16, I have x to the 7th. With x to the 7th, That's going to give me x to the 6th. It's odd, so I take the most amount of evens that I can out of it. And then over here I have x to the 1st. So I'm taking the 7, splitting it into the most amount of evens I can, and then the leftover one. We know the rule for evens is divide by 2, and then the radical x, there's nothing we can work with. So every time you do an odd exponent, you're going to end up with an x to the 1st. Let's go ahead and take a look at number 15. 15 changes up a little bit here because the number under the radical is not a perfect square. So when we get into these that are a little more challenging, when I split this up, I automatically start working with two separate radicals. Everything in the first radical I'm going to put as perfect squares, and everything in the second are going to be not perfect squares. So when I'm looking at just this 45, we'll start here. I know 45 is not a perfect square. However, there is a part of 45 that is. So if I look at the factors of 45, I know that it's 9 and 5. I'm putting the 9 in the first one because it's the perfect square, the 5 in the second one because it's not a perfect square. And then I want to go in and I want to do the same thing, but I want to look at this x to the 9th. If it's odd, it is not going to be a perfect square. So I'm going to have to split that up. I'm going to do x to the most amount of evens I can get, which is 8, with an extra x to the 1st over here. When you get to this point and you've separated everything appropriately, every single thing that's in your first radical should be able to be square rooted. So square root of 9, 3. Square root of x to the 8th, x to the 4th. Everything that's in your second radical is unable to be square rooted and stays the way it is. So 3x to the 4th, radical 5x is my final answer. And these problems can get much more difficult as you go through. I'm actually going to go ahead and jump down to question number 21 now. In question 21, we do have something outside in the front of the radical, and we talked before about how that's connected with multiplication to the radical, and you essentially carry it along until you find something else out in front of your radical. And then we can multiply it together. So if I start looking inside the radical right now, I can see that I have a 90 in here. 90 is not perfect, but its factor of 9 is times the 10, which is not. So everything here is a perfect square. Everything here is not a perfect square. And then I'm going to do the x to the 3rd. So if I'm looking at this x to the 3rd that's right here, not a perfect square, but x squared is the most amount of evens with an extra x. And I'm just working my way through here, and then I'm going to go to the y. That's technically y to the 1st, so that's going to go over here. And then I have that z to the 16th, and with z to the 16th, that whole thing is going to be a perfect square because it's even. So when I get to this point, I want to go through now and simplify what I can. So in here, the 3xy squared that's out front stays where it is. Remember, there's multiplication. I'm square rooting everything in the first radical. Square root of 9 is 3. Square root of x squared, divide by 2x to the 1st. Square root of z to the 16th, z to the 8th, divide by 2. And then this radical 10xy, I can't do anything with. When I get to here, I have to go back and multiply these together, the two that are out in front. 3 times 3 is 9. X to the 1st times x to the 1st, x squared. Y to the 2nd. Z to the 8th. Radical 10xy. So the section in here, when I actually multiply these two together, goes back to your rules of working with exponents from last year. Just as a quick little reminder, if you have x to the a times x to the b, the rule for that is that you're going to add those exponents together. So you're adding them together. Also included in today's notes are adding and subtracting radicals. I am going to stop now, though, and do the adding and subtracting in a different video lesson. So please continue on to the next one. I'm just going to stop this one now, give you a chance to kind of regroup, and then you can start on the next video lesson, adding and subtracting radicals.